Hello, welcome back from lunch. All right, we're going to move right on to our next session. It's from Watney Robotics, and so they are doing telepresence. And I think over the last couple of days, we've kind of come to realize that in one form or another, direct control of robots is going to be necessary, whether that is for teaching robots how to do things, or even more likely, I think, when we get robots out into the world in semi-structured or unstructured environments, they are going to need our help for the foreseeable future. And hopefully that's what Watney Robotics will enable us to have. So, take it away.
Hi everyone, I'm Ryan, and this is Sean. We founded Watney back in this past January. I just graduated from Penn, studied finance, CS, and robotics, and Sean dropped out of Berkeley Eats. So we build robot employees, and today we're going to be talking about how we can get useful robots deployed into the real world as soon as possible. This is Watney. We founded Watney this past January, as I said, and this is our wheeled bimanual robot. It's either teleoperated or autonomous, depending on the task, whichever makes sense for the task at hand. We founded Watney with the core principle that with teleoperation, we could accelerate the adoption of robots by many years. I'm going to start off with a story about our first deployment, and it all starts off with towels. So my neighbor from back home was complaining to me about this resort she loved. It's a fantastic place, great amenities, and a really friendly staff. The issue? Every time she hopped out of the pool, there wasn't a towel waiting for her. It was a pretty bad way to start your morning, right? So this sounded pretty interesting to us as we were starting the company, and we decided to do a site visit. It could not have been more ironic. So when we got to the lobby, we saw the entire front desk staff all folding towels instead of doing their actual job. And when we were walking around, every couple corners, you could see people folding towels instead of doing their actual job description. It seemed like a really weird way to allocate labor, and we were pretty interested. When we talked with the resort management, the issue turned out to be so much worse than we originally imagined. So not only was this a huge distractor for their staff, it was causing lots of injuries. Every couple months, someone would get a back or a shoulder injury with a workers' comp claim of up to $50K. And for hospitality businesses, that could be your entire margin for the month. More importantly, this is someone who can't pick up their child anymore. So this was so obviously a flawed way to allocate labor. And we see in every corner of the physical world, people are putting humans into unnatural and expensive occupations that just doesn't have to be. So Watney was founded to solve this exact problem, not in the distant future, but today. This is our teleoperation system, and this is me telling Sean to fold faster with it. So what you see here is a VR display and a scaled down kinematic replica of our robot arms. So not only does this allow you to control the robot intuitively, it allows you to control the robot from anywhere in the world real time. So we've written down that latency gap to make it so that our operators from the Philippines can control this robot pretty much anywhere in the world real time. Now, why does this matter? This allows the operators to operate with a level of comfort, precision, and efficiency that was previously unparalleled. So traditional teleoperation systems feel like you're trying to tie your shoelace while watching yourself through a laggy video feed. Our system feels like you're looking in a mirror. Basically, teleoperation allows us to accelerate, right? If you think about Waymo, for instance, imagine if Waymo was able to remotely drive cars. They would have been able to deploy a decade earlier when they had solved self-driving to 2 nines of reliability instead of 6. But here we are 10 years later, finally getting deployed. Think about how many lives would have been saved if they would have been able to deploy earlier. We think robotics is too important to wait for full autonomy, and that's why we're pursuing teleoperation. So, going back to this resort story, when we were talking with them, one theme kept popping up. Robots cause more hassle than they're worth. So, they had tried a mix of robotics ranging from autonomous tray tables to drink prep. And these were all 99% solutions. So, this drink prep required someone to go in and clean it every day. The autonomous tray tables were treated more as just like a little cabinet on the side eventually. It's because they still required a human to do that 1% that the robot couldn't. And that's where teleoperation comes in. Here you can see this overnight time lapse of our robots deployed at the resort. So they fold 20 hours a day and charge for 4. This is pretty crazy, right? We're still surprised by this. So you might be wondering about some of the implementation challenges. Beyond us forgetting to put a battery charger there on the first night and the robot's dying, that's solved. But there's been a lot of instances where the robots have to do tasks that are completely out of scope. So for something that's supposed to just fold towels and move bins, there's lots of situations where a cabinet swings open and blocks the way to the charger, or, for instance, the dowel on Robot A's gripper popped out, and teleoperator A was able to tell teleoperator B to come in and press it back in, thus avoiding huge maintenance, escalation, and just like a bad UX. Right? This is only possible when you have human common sense in the loop. If you're a model that sees a cabinet swing open for the first time, you're like, oh my god, what do I do? But for a human, it's quite simple. You just use your common sense. So hospitality might sound like a low stakes, low pressure environment, but we're also in conversations with some of the biggest, highest cost of failure, most important industries in the world. And it really comes down to this. When you're deploying robots into very important tasks that are very unstructured, having a human in the loop becomes even more important. All of these industries know they're not quite ready to fully trust autonomy yet, but they're ready to trust humans because they already do. So when you think about a robot that has human oversight, a human looking over its shoulder that's able to intervene at any moment, that's actually more trustworthy than a human operating by themselves. So you get the consistency and the precision of the robot added with human judgment and accountability. And this is why some of these organizations have started to trust us. They believe in this hybrid approach where you have a human come in and solve what the robot can't, but you have the robot do things much more precisely and accurately than a human ever could. So I'll give you an example. Think about cooking. Would you trust a robot right now to fully autonomously cook chicken in your house? To not start a fire, to handle raw chicken, to understand cross-contamination risks? Probably not, right? But would you trust a robot with full human supervision, 10 millisecond response time? That's a little easier to swallow. This is an example of one of our deployments in a kitchen where the robot is cooking some paneer curry. Now, Sean likes to joke that Watney can cook better than I can, and unfortunately I don't think that's a joke. It actually tasted pretty good too, so we'll let this play. Cooking is one of those real-time tasks where if you screw up any part of the process, you have to start the entire thing over again. You burn something, you spill something, requires a complete environment reset. That's where having teleoperation to help correct models is really, really important. And he goes ahead and puts it on the plate. So we like to keep our talks short, and I'll leave you with one question. I encourage you to think about all of the places in your organizations where humans are stuck doing unnatural, repetitive tasks. In a warehouse, this could look like doing repetitive lifting, causing back issues. In a wet lab, this could look like doing repetitive pipetting tasks instead of actually having skilled technicians do analysis. These are both areas of work where all of that human energy and creativity are being put to waste. So think about what your organization could do if humans were free to do what they do best. Solving complex problems, building relationships, and making strategic decisions. Thank you. And we're open for questions.
Awesome. Well, if anybody has any questions about our tech, our deployments, we're happy to reserve the rest of our time. Yes.
What were the challenges you encountered when you get over
There's a mic right over there.
So I think the question was, what were the challenges in building the teleoperation system? Yeah, so I think there's a big difference between getting a telop system working in the lab versus getting it working reliably in the real world. There's all sorts of adversarial network conditions that you run into. So, you saw that, let's go back. This is in a basement, basically in a concrete box. And getting it to work reliably when you have 50% packet loss, really terrible Wi-Fi conditions is quite challenging. So I think getting it working in the lab, to say again, is quite easy. Getting it working reliably when all of this unknown stuff happens to you out in the wild is quite difficult.
I was curious, why did you choose to use encoder-based teleoperation rather than VR and hand tracking?
So we actually do a mix of both. That example uses joint-based. What we found is for different tasks, end effector space and joint space control differ wildly in performance, and our optimal solution is really just to use task-specific teleoperation interfaces. We so far haven't found one that is perfect for all flavors of tasks.
If you're teleoperating, would you say the biggest challenge right now is just network at this point, or is there any robotic problems that you think needs to be solved?
I think one of the largest unsolved hardware challenges are hands or end effectors. We still don't have great commercially viable hands, and one-DOF grippers still are too limited and constrained for unstructured tasks. Thank you.
So I've used a lot of telepresence robots, just kind of tested them out, and I think some user experience is often underemphasized, and you can spend a lot of money having a great user experience on the user side, but that's probably not sustainable for a product. So how do you balance that?
So I think money hasn't really been a limiting factor for good UX. A lot of it is both the speed of iteration and also being able to clock the sheer volume of teleoperation hours and get feedback from our teleoperators on how to further improve the system. You don't actually need super expensive $100,000 teleoperation rig. You really need to design for the teleoperator experience, for teleoperators who operate these robots 8 hours a day, not an undergrad student teleoperating for 30 minutes a day doing data collection in the lab. And that's really what our key focus has been.
Typically what some complaints are is our teleoperators will be teleoperating for like 4 hours at a time. So in our first iteration, they would get a bunch of motion sickness and not really be able to teleoperate for more than 15 minutes at a time. So we had to completely re-engineer the perception and display process to make them more comfortable for them. And then there's also a bunch of stuff where like sometimes they want to execute a motion that they feel the device is fighting them on, and that's something you have to redesign for that use case.
Hello. So I have like 3 parts to the question. One is, what have you experienced in terms of like using a gripper with like a claw-like mechanism versus the actual digits? How do you think of that, and what would be the most effective design from that perspective? The other one is, what could be the potential payload capacity of these kind of robots? And third is that in actual like conditions, whether it's indoors versus outdoors, how are you guys planning to do this? Are you focusing on the indoors or also doing it for the physical environment?
All right, so I think the first question was around design choices for one-DOF grippers, and I think so far the biggest lever on improving teleop performance has been designing special purpose fingertips, ones that are shaped specifically around towel folding, around picking up large round objects, things like that, which I think is the unfortunate reality when you only have one DOF on your end effector. Second question.
The payload.
These arms are rated 5 kilograms in all orientations, 10 in most. Payload really hasn't been a limiting factor. For a lot of these types of off-the-shelf commodity hardware, really what matters is the actuator dynamics, specifically how much stiction and how back drivable they are. not so much the payload capacity, especially when you want compliant impedance control. We've driven the robot outdoors plenty of times. I think for the specific AGV that we've used, we haven't really had hardware limitations going indoors and outdoors, and our entire network stack is designed so that you can operate this basically anywhere in the world. We run off of cellular, Wi-Fi, and Starlink, and as long as one channel is available, we can operate it in the middle of downtown San Francisco or in a basement.
Yeah, and when we transport our robots and U-Hauls, we just have the teleoperation feed live so we can monitor them, and it works the entire highway, just to give you a sense.
Thanks.
I think we have time for one more question. So yeah, the system can run air-gapped as well. That's just very custom for that particular type of customer. Thank you very much.
All right, on to space robots. All right, so next up we have Sean Azimi, who leads the dexterous robotics team at NASA's Johnson Space Center in Houston. These are the folks who are responsible for some of the absolute coolest looking robots, I think, over the last decade. You've got Robonaut and Robonaut 2 and Valkyrie, and I have to say that Valkyrie is one of my favorite robots because among many other things, like it's one of the very few, maybe only humanoid robots that was deliberately designed not to be like some pseudo dude. And I really appreciate that there's at least one of those out there. And now I hope you were here yesterday for the Space Robots panel, because it's always fascinating to hear about Sean talk about robots in space, because it's such an extreme environment and all of the requirements and constraints are just totally different from robots that are designed to operate on Earth. But at the same time, you can actually learn a lot by thinking about designing space robots, even if you're not designing robots for space. So I'm very excited to hear from Sean.
Awesome. Thank you so much for that introduction. Good afternoon, everyone. I want to thank the folks from Watney Robotics. That's a really good setup, actually, for my talk, because we're going to start talking about a little bit of teleoperation and the power of that. I'm Sean Azimi. I'm robotics technical discipline lead and engineering director at NASA Johnson Space Center in Houston, Texas. In Houston, as you all know from Apollo 13 and other media, it's the home of the astronaut corps, the home of mission control. So we are focused primarily on robotics that support humans exploring space. I want to start my talk today with the dedication to my colleague Lyndon Bridgewater. He is truly a pioneer and one of the kindest souls that I've ever met, and we miss him dearly. So we'll start the conversation today with a question that is recurring, which is humans versus robots in space. There are a lot of aspects to this question, but I want to start out by considering some of the strengths and limitations of both. So we'll start with the astronaut. So looking at astronauts in space, humans are, as we all know, very adaptable, intelligent, resilient, able to take on many unknown challenges. Is one of the reasons why teleop is so powerful. But working in extreme environments where we need environmental protection, the environmental protection, in this case a spacesuit, when we're going outside, EVA or spacewalks, is a limitation, right? It limits our ability to move primarily because a spacesuit is basically a big balloon. You can see the resting pose for astronauts is like this in microgravity, not because they're doing a zombie walk, but because that's the relaxed position, right? Anything else you do with your arms, to bend your arms or close your hands to grip something, that takes work just to compress the gas, right? And add to that very thick gloves that have many layers of protection built in, and that reduces your dexterity. Looking at the legs, bending the knees, there's not so much use for legs except as an anchor when you're in microgravity. So astronauts are limited by that. But in spite of all that, they're able to do a lot in space that we can't do with the robots that we currently have on space station. You can add to this, right, so the risk of cutting gloves, that creates a potentially lethal risk for depressurizing the suits. And even looking back at Apollo, it's very fatiguing, right? Spending hours in a spacesuit working, it's work constantly, it wears on the body, and while it's a tool that's very powerful, we want to use it on only the most important tasks. Looking at robots, right, we have ways to overcome some of those limitations. We can adapt the robot to the environment to be able to work without requiring the protective covering of a spacesuit. That allows the strength to be fully utilized, the dexterity to be fully utilized. And in addition, robots can be adapted to the environment. For example, Robonaut 2 was adapted, as you can see, in microgravity to have climbing legs, right, that look much different than walking legs, but are adapted with these special crab claw grippers that interact with the same handrails that the astronauts use both inside and outside the space station. So it's a key aspect to us that robots can operate in human environments designed for humans using the same interfaces and the same tools, right? So we don't have to have duplication. But that's an adaptability. But of course it comes at the cost of complexity, right? And I think the point was made perfectly, right, saliently. If the robot takes more crew time to set up and maintain than what it saves the astronauts, that starts to eat into the reason why you have the robots out there in the first place. So you need to have very reliable robot systems that are maintainable in the field. So I say, if you take a look at that first, but with a different perspective, it's more about robots and humans working together than one or the other, right? The two can be complementary to each other. And I'll give you an example. So looking at International Space Station was assembled in space from many components built by many nations. And there were many parts of it that were designed to be deployed automatically, but that doesn't always go right. You can see there's a big tear in one of the solar array wings. So we had to use a team of human crew members and robots to be able to address this, right? This is a big concern for space station because this is the source of the space station's power. If that array were to tear further and separate, they would lose a significant amount of power. So they sent astronauts out. We had, of course, in our operations, right, it's not just the crew member out there on their own. There's hundreds of people on the ground, engineers and flight controllers and other space professionals that are supporting them, that are in the room. You've all seen Apollo 13, you know some of the engineering backroom stories and support. But there's also their fellow crew members who are inside, right, in the IVA environment that are operating the robot arm, right? So we already have and demonstrated these combined human and robot operations successfully, right? But we had the whole reason we had to do this EVA was because we didn't have a robot that was dexterous enough, right, to be able to tie together the cord that would cinch the solar array to prevent it from tearing further. So I think this is a case where these kinds of incidents inspired the idea within my organization for the predecessor project of Robonaut 1. So Robonaut 1, the idea was that what if we had an EVA assistant that had the same dexterity and perception, right, as a human, could use the same interface as a human, that could be a persistent asset that we could assist astronauts who are on EVA, and maybe even save some EVAs altogether by being able to send out the Robonaut. Of course, I mentioned adapting to the tools, so in this case, the tether hook and pistol grip tool, kind of the space drill. So these are the tools that are already certified for use for EVA and have compatible interfaces for the crew to use. That's one of the reasons why Robonaut took on the humanoid form to begin with, at least for the upper body, right? The idea of bimanual, 2 arms with dexterous hands and a head with sensors that you can point, right? But the bottom, right, the body, that was adapted to microgravity from the beginning. It's single tendril in this case, and then with Robonaut we had 2 legs. But power of teleoperation, right? This was late 2000s, before everyone had VR headsets. But it's amazing what you can do with that, right, to overcome the edge computation limitations. And in this type of application, where there's an astronaut inside operating a robot outside, you don't have to worry about the communications limitations and latency, bandwidth issues, comm outages, things like that. Fast forward to today, and there's that guy doing much the same thing with a different robot. So I'm the lead of the dexterous robotics team, among other things, and my team is focused on using the Valkyrie humanoid today and other robots to do feasibility studies, look at what are additional things that we can do with robots in space to support our new exploration architecture. And so we've got new places to go. We're going farther than ever before with our new Moon to Mars campaign. And as you can see, you get farther and farther from home. That creates issues that makes things more difficult in terms of both transit time to get new material and people, as well as the communication limitations that I mentioned earlier. So looking at comparing Apollo, right, what we're doing now with Artemis is different than Apollo. All the Apollo missions were equatorial on the moon and lasted for hours, not weeks. Single lunar day, right? So sunlight going overhead. Whereas Artemis is lunar south pole, so like the South Pole on Earth, we have the sun at a very low angle going around, and we have very unusual conditions there, limitations with visibility to Earth, right? Because we're right on the edge. There's a little bit of a wobble in the way that the moon rotates, and it's extreme terrain. So just to give an idea of scale, my home city of Houston would fit entirely inside of Shackleton Crater. And if we compare Malapert to Mount Everest on Earth, that's an even greater terrain relief going down to the crater. Another comparison, Grand Canyon to Shackleton, you can see much bigger scale. But this is part of why we're going, right? These regions, especially inside of the many craters that are large and small, never see the sun. And because of that, there are volatile compounds there, resources that are valuable that would otherwise be sublimated into space instantly were they to see sunlight. But that does put us in, it's a little bit hard to see on the thermometer there, but the red line shows from 40 to 110 Kelvin, and that's among the coldest of the temperatures that we would see in the solar system. And then of course if we're in the sun, right, we have much higher thermal loads. So it's really a land of extremes in a lot of ways. But as I mentioned, that's why we're going, right? There's a lot of resources that are there. That's one of the main reasons why we want to visit the South Pole. So everyone knows Starship. It's the human landing, one of the human landing system options. Have to zoom in a little bit to actually be able to see the crew members down at the bottom there on the elevator. And in early missions, it'll be lander, crew go EVA, they walk outside, they take some samples, they go back up, they leave. But in later missions, we're going to have a rover that enables the crew to go farther. This is the lunar terrain. This is the Apollo LRV, but lunar terrain vehicle is the new version of that. And then eventually there's going to be a habitat, right? We're going to establish more of a presence, permanent presence on the moon where we reuse surface habitat assets. But as soon as we do that, that creates a new limitation versus Apollo, where we have to resupply, right? We have to get rid of the trash. We have to bring in all the new supplies, all the new food, clothes, spares for their EVA suits. It's a lot of stuff. And you can't put the habitat right next to the lander. You know why? Because the lander's gonna blast it, right? Anybody who's seen the Starship takeoff or landing videos, you want your habitat to be far away. It might be 5 kilometers away, right? So now you have to get the stuff from the elevator, right? The elevator will bring it down to the surface, but how do you get it to the habitat? You have to load it onto the rover and then unload it from the rover, move all of the cases through the airlock or into the cabin and be able to do that exchange. That might be multiple EVAs. So that's where we see kind of the value proposition for robots, especially remotely operated robots in advance or between crew missions. Because otherwise, if we send our crew members, we're giving them a lot of stuff that they've got to move, and then we're going to have them do some maintenance because there's lunar dust, and we're going to cover up our solar arrays and our radiators. Maybe we'll add a little bit of assembly connecting up their power unit to the habitat, and that's before you even get to the science, which is the reason that we sent them in the first place, right? So anything we can do to get ahead, right, even if robots go slower, in the 11 months out of the year the crew aren't there, that's a huge value add, right? That's billions of dollars. Like if you look at the labor cost on the surface of the moon, it's very high. I don't know exactly what it is yet, but it's very high. But I think space exploration needs many types of robots, right? They might be single manipulators that are integrated with the interior of the habitat to move logistics inside. In microgravity, we might have free-flying robots, right? ISS is going to be retired eventually, and they'll be replaced by commercial space stations. So free flyers are really good. This is Astrobe that's actually designed and built here at Ames. Gives a great sensor platform. They might be multi-limbed robots that climb, right, and can move logistics and do other tasks, or bimanual, mobile manipulators that have different types of platforming. Whatever magic carpet gets the arms where they need to be, right? But there's limitations, right? There's gaps from terrestrial to space. Terrestrial, we have more control over the environment. There's the possibility of intervention with a lower cost. But in space, we just have environments. This is an actual picture from ISS, by the way. We have kind of the space version of hoarding. If it costs a lot to bring more stuff, you're not going to get rid of any of your stuff if you don't absolutely have to. And that's the situation we have on the International Space Station today, that we have lots of stuff. It crowds all the open spaces. And of course, we're not going to plug things in. So we're going to have lots of cables. The lighting is going to be iffy. It's a very difficult robotic navigation problem. Dealing with soft bags, right? We use soft bags because when you empty them, they compress and you get them out of the way. If you have a bunch of hard cases, it's not going to work. But that's hard for robots, right? Dealing with something that's deformable. So these are all challenges that we see adapting. And one of the ways you can learn more about that is to look at, a lot of people don't know, I got a couple links on these pages, so it's good to get your cameras out. Otherwise, you can let me know and I'll send you these links. But NASA has a Moon to Mars architecture, which we update on an annual cycle. It has an architecture definition document, which lists the elements like, lander, habitat, logistics is a new element. And that has use cases and functions, and that's where robotics and automation can fit in. There's also white papers that give more of an in-depth look at some of the key technology areas for NASA, some of the key use cases and needs, right? But still at a pretty high level. Looking at technologies specifically, right? NASA has a mission directorate called Space Technology Mission Directorate. It's responsible for what its name says. They rank annually what the technology needs that they feel are the most important, which reads, what do we fund today versus tomorrow, right? So I recommend taking a look at those. Of course, these days, right, I think people sort of assume, right, NASA's doing all this stuff, but really we're not. It is truly a coalition and a partnership. Commercial, international, academic, interagencies. I think our universities are the wellspring of all of our innovation, and startup businesses are what commercialize those technologies. We explore together. Internationally, we can't do it alone. So it's important for us to be able to establish and maintain these partnerships. To that end. There is many of you know, NASA has a Small Business Innovative Research, so does Department of Defense, National Science Foundation. It's our seed fund, right? So this is, if you're looking for funding, this is where you would apply as a small business concern. It starts with a phase 1, which doesn't seem like a lot of money, and it isn't. But that paves the way to a lot of different opportunities down the road and ways to build relationships with NASA programs in the future. The subtopics have been released at the beginning of this month, and the call itself will go live in January. You'll be able to submit proposals, so I recommend taking a look at that. And that's all for my talk. feel free to reach out to me on LinkedIn. Happy to connect and discuss any kind of partnership opportunities, or just connect you all with, I feel the mission of my group is to help demystify all of the things about NASA that are a little bit opaque. And there's a lot of information that's out there that is actually public, but it's hard to find. So we're here to help you find that kind of stuff. So thank you very much for your time.
We have time for a couple of questions, and if you're on the next panel, can you go to the back and make sure you get your mic? And yeah, who's got questions for Sean?
They're sleepy.
Somebody has to be first. Oh, okay, yeah.
You can go right there. I'll repeat it.
How does NASA think about choosing what to use full autonomy versus having a human or on-the-ground or an ISS operator robot to do it? Is there a strong preference to make sure that both go to the EDAs, and how do you guys decide?
That's an excellent question. So the question was, how do we decide at NASA whether to go full autonomous versus teleoperation? And the answer is, it depends on the application, of course, right? What our communication limitations and other drivers are. But I like to say that I prefer a scalable approach, right? The idea of having, starting out with lower degrees of autonomy, more human intervention or supervision, and building up over time, right? Because we have difficulty simulating all aspects of the in-space environment on the ground, either in computer simulation or in test facilities, right? And there's always something unexpected that will happen when you're out there. So having the ability to learn and implement autonomy where we're really good at something, but then be able to fall back if something goes wrong, I think, as y'all pointed out in your talk, is very, very powerful.
Have you guys had extensive exploration with non-deterministic systems where you have end-to-end manipulators, but you can't actually reason around whether this will do the thing when you invoke it?
That is a big challenge, right? So yeah, for space flight systems, we have the concept of certification, right, and testing and verification and validation. And it is an emerging field right now of how we do that for example, machine learning techniques, or something that doesn't have a directly demonstrable, like fixed input to output state machine type of. So it's something we're working on. But I think, as folks point out, right, that humans are the same way. We demonstrate through training and testing rather than understanding every neuron.
What do you think is the main constraint to getting like thousands of robots building structures?
I think the main constraint is it's a couple things. It's money, right? Investment, because it's a niche application, right? It's harder to see the market, right? That if you're only going to sell a few units. So I think bridging that gap from terrestrial, like what y'all are doing, which is, I think, foundational, right? And then getting that model to translate to an in-space application where we can realize some of those advanced capabilities with not $1 billion robot, right? And part of that has to do with, I think, something I was pointing out yesterday, is that you can't have trial and error without error. We have to be willing to accept that sometimes they won't work out, right? And we'll need to send another one. And I think the incremental, especially if you all demonstrate in low Earth orbit, right? It's a much lower cost than if you jump straight to Mars, right? So that incremental approach, I think, is key.
Thank you very much, Sean. That was awesome. And if our next panelists can come on up, please. So we'll be talking about applying Gen AI to humanoid robotics. And as with the panel this morning, if you folks could just kind of introduce yourself briefly and then talk about why are you here? What do you do with humanoid robots and generative AI?
Cool. I am Russell Nickerson. I have a startup called Collabots. It's kind of a consulting thing. My day job is actually Mass Robotics. A lot of people have heard of that. It's like a nonprofit co-working space in Boston. But in the past, I've worked for SoftBank Robotics on the Pepper and Now robot humanoids, and I'm helping a Japanese startup right now on an entertainment humanoid. So just really interested always in the industry since I was a kid, and it's great kind of, being here on stage and living the dream.
Hey everybody, I'm Caitlin, or CK. I was driving down from San Francisco, and I think I'm probably the person at this conference who's worked in robotics the least amount of time. I worked in robotics for 1 month as of Tuesday, but my background is high volume, high complexity consumer electronics. So like AR, VR, computers, and things like that. And so I recently joined OpenAI to lead hardware in robotics, and I'm really excited to be here and to learn from all of you.
So I've been in robotics a little bit longer, I think just over 20 years this year. So I started out at Carnegie Mellon. My name's Pras Velagapudi. I'm the CTO at Agility Robotics, which hopefully needs an introduction after this morning's keynote that Jonathan gave. So I spent the first 10 years of my career in academia at Carnegie Mellon working on humanoids, drones, snake robots, all sorts of fun stuff. And then spent the next 10 years of my life in industrial automation, living in warehouses and making robots actually do stuff. And then kind of reconnected, joining up with Agility, when kind of those two worlds met at a particularly interesting time in the industry as we're all here today. So I'm here because Agility obviously is very interested in exploring and deploying these new generative AI models and technology.
Very cool. Kamate Richards, I'm here with Amazon, but actually more of a personal reason. I am working on a little stealth startup in robotics, in home consumer robotics. But for Amazon during my day job, I really focus on building products, consumer-grade products for generative spaces. So you can imagine we had a lot of interest and hype train around GPT, those kinds of things. But it took building applications on top of it to make it truly viable. So that's something that we really focus on at Amazon.
Kamada, maybe you're the person to start then. Like, where are we with generative AI in robotics right now?
I'm going to exclude talking about the foundation models, as we had that talk this morning. I'll say that the space is wide open from code editing, code assistance. Some of these things are unsexy, but they're absolutely vital. Things like documentation, you can use generative AI to document your processes. Other things you can do is handle exceptions where your reinforcement learning models aren't working. You can step through with a generative model and have that model kind of adapt to the circumstance, and that's particularly good in pick and place robotics. Rather than falling back to a teleoperation, you can use generative AI for that purpose. My particular interest is in automating the robotics software development lifecycle stack. That's my interest. To that end, last year I created Gen AI created an application that took a Boston Dynamics Spot robot, built the interface to the robot. This is Gen AI doing that. Built the front end, so I didn't build the front end, it built the front end. And then that front end was in Apple Vision Pro. And then we turned the robot on and it worked. Like that to me is where we are today. I believe that's the standard. But there's so much more, I'm sure some others have dealt with some other stuff.
Yeah, and Pras, you have robots using Gen AI and they work, right?
Yeah.
To some extent. I mean, I think there is a bridge there in terms of the reliability and determinism of using Gen AI in these technologies. And we think about, we certainly did demos where we integrated a VLM to automatically generate the tasking to run in real time on the robot, or diffusion policies for motion generation, kind of like the foundation models that were being discussed this morning. But there are these intermediate steps that are kind of on the way there and very realistic. So for example, we have our Agility Arc cloud platform where we're hand authoring task workflows. And one of the really promising areas is, well, you can semi-automate that generation and say, hey, give me a human description of what we're supposed to do in the warehouse here. Move yellow totes to the left and red totes to the right. Let me turn that into tasking that Digit can do. And a human can still approve that and say, yes, upload that to the robot and start running. And those entry points are really very short term right now, even as we work out the kinks of like, well, exactly how are we going to grasp the tote, and is it going to be grasped exactly the same way through a diffusion model, you know?
How has that experience been for Agility? I mean, is it something that is been easy for you folks to integrate into your workflow, or is it a completely different process?
I'd say it's been both better and worse than we anticipated. When we shot our video last year on YouTube of Digit clean up this mess, we took a voice command and Digit used it to basically pick up trash off of the ground and put it into recycling bins and trash bins and so forth. It was so fast, we did the entire demo within 2 weeks because a VLM could essentially really quickly pick up on the skills API that the robot already had. And it had some really surprising stuff that it figured out on its own. Like, for example, it picked up bubble wrap and threw it out in the trash, and we thought for a while that that was a bug. But it turns out that actually that bubble wrap was not recyclable. Like, it's the type of plastic that's not recyclable where we were running the robot. So that was really semantic knowledge that was getting captured in a very, intuitive and natural way. And that was great. But then, sometimes we'd ask it to do stuff like move around boxes or things like that. One of my favorites was we did the clean up this mess demo at one point while we were testing, and it's like, well, step one is I'm going to put the garbage bin in the garbage bin. And then it started going over to the garbage bin. We had to e-stop the robot because it was about to do something really strange. And that, is that kind of gap where it does amazing stuff sometimes, and then it does really surprising and undesirable stuff other times, and really figuring out, well, how do we turn this into something that we can put into production? And part of that might be some amount of human-in-the-loop approval or editing in the same way that we use CodeGen right now, and some of it might be this work that's being done with, just in general in the industry, to improve the quality of the outputs, to basically refine, do chain of thought execution to basically produce better, more consistent outputs.
And Russell, have you had a similar experience?
I mean, when I think of all this stuff, I think of like integrators in robotics. That's the big kind of linchpin for a lot of deployments. So in the industry, it's really hard to get that right integrator or that problem. A lot of big name companies come out and they say, hey, I have an issue. We're running a challenge with Chewy right now. They have heavy 50-pound dog food bags, and they don't have a gripper, they don't know what robot. Using Gen AI, that can enable integrators to find solutions quicker. Not that they necessarily wouldn't find it before, but it gives them more options and more direct kind of connections on that front. I think it's always similar to you're saying, sometimes it doesn't come up with the best idea. Being pragmatic about, okay, let's not just blindly follow and say this is the perfect, this is gonna come up with every best answer, but give me some ideas to solve solutions in robotics. I think that's gonna help move forward the industry, and because typically, again, sometimes there's a lot of back and forth with find me a solution, and then they try it doesn't work, and sometimes they give up to wait for the industry to catch up. But it's kind of a boost to the industry for OpenAI.
Caitlin, if you're willing, I would love to know just what your first impressions are of how robotics has been using this technology, and what you think opportunities might be.
Well, one of the things I've learned is these emergent properties of AI as we create new models. And so that's an area I'm really watching, because there was an example where ChatGPT-2 wasn't trained to do translation, and then somebody just randomly, inside of OpenAI, asked it to translate something from French, and it did. And so this is an area that I'm really interested in, actually, is emergent properties and what happens as we go from model to model. Obviously, a lot of people are already using our models and other models on their robots. my goal is to make that work better. And my goal is to make, really at the end of the day, my goal is to make better models so that when you do use them, they just work more of the time. And so I'm really excited, I think, to work with this industry and to start to get to know many of you to try to figure out how we do that. Because the truth is, as exciting as AI is, and you might have seen me have a couple releases this last week, it's at an exciting place. All of that's happening on 2D screens essentially right now. All of that's happening in computers. And I think it would be really incredible to have the benefit of AI enter the physical world more and more and more.
And we've talked a lot about data over the last day or two, and that's something that I think we should certainly talk about on this panel. Caitlin, either you or anyone who has something to say, but just where are the data sources for training these models, and how careful do we have to be about where that data comes from, and just how constrained are we by this data availability?
Yeah, I think the answer is we are constrained by it. I'm really interested in learning about the modalities of data that we actually need to feed to the AI models, like what is the data type that we need, and what kind of latency between the data types we can accept. And that's all kind of open questions in my mind. So I'm very excited to see what kind of data we need to inform. But I think it's pretty clear that the better data we have, the cleaner the data we have, the more consistent data we have, the better the model will be, and the better then it will work for our friends in the rest of the robotics industry.
I think that. Oh, I was going to say just real quickly. So, OpenAI is a great example of taking a transformer and providing an application on top of it that was distributed to everyone, so we all have access. They had transformers before. No one cared. Not no one, like the common person didn't care. And so when we got OpenAI and maybe it hallucinated a little bit, we didn't care because we were getting something fabulous, fantastic in our hands for the first time. That can't exist in both enterprise, it can't exist in robotics. We can't have models hallucinate and give back bad values. So I think the closer we can get to, and actually I believe this whole space, it's kind of its infancy, because we're starting to see layers upon layers of services that are stacked on top of these models that then provide that consistency, that provide that security, all the things we need, compliancy, policies, all those things you layer on top of the model. So I don't think that a framework model is going to be end all be all. I think it's going to be a framework model plus layers, just like we do it in OpenAI and Amazon Q and all these different things. We layer on all of these like structured outputs. We layer on multi-agents. We coordinate agents, orchestrators, all these things. Code generation, the ability to kind of look back and see if the code is correct. Recursive criticism. We layer on all these things to make OpenAI better and the tools that we have better. I'll stop there. That's my minute. It's a minute.
I'd love to add one thing to that is also that it's not going to be necessarily language models that are the most useful for us in the robotic space. I think that it's going to be several different models together that inform the space.
I think right now we're at this interesting point where we know we need data, and also simultaneously everyone has realized that data is extremely valuable and needs to be protected. And so, one of the things we experience is in being able to build out our data sets, which we like to share with other players. We're not trying to build our own large models. We're trying to work with other people to build those models. But there's this stack of authorization of the provenance in a way that's kind of unique to this space, because it comes at a point in time after everyone realized this import. There's no, Project Gutenberg of robot stuff. I mean, there is, like, OpenX Embedded is maybe a small version of that, but nowhere near the scale that we have. So we're like trying to license our data all the way up. And then there's also this question of what is the right format. Unlike large language models, which quite literally have a lingua franca, robotics models have a lot of different options in the modalities that can be represented. How are we representing forces, joint space, perception information? And if everybody builds their models up in incompatible or poorly curated ways, you end up with this kind of like data soup that might not really be the best or fastest way for us to build a useful representation at this level.
Those are excellent points. So what do we do?
Well, I can talk about what we're trying to do, which is to get the best synthesis of what folks like OpenAI and other players in the space are asking for, and to provide the best synthesis as one of the robot providers in the space, and looking at what others are trying to produce in terms of the modalities of the data that seem like they make sense, and build up our data set that way. I don't think that's the end state. I think we're still very much discovering what needs to be done there as ourselves and lots of the other folks that presented at this summit, are evolving our technologies. We'll have to kind of solve for that and figure out what is the right data representations and the right ways to exchange, license, and curate these data sets.
If I may as well, it seems like, to me, just as a mental, an exercise mentally, that if we can simplify some of the variables and the differences between the systems, that it's likely that the AI models we train will get trained better and be then more useful for the models that follow some of those same standardizations. It's probably too early to do any standardization now, given where humanoids are, but my sense is, at least with the sensing cluster, and potentially some of the ways that we think about nuxing different data types together, it could be an interesting place to look at the future.
One thing, we look at like the evolution of mobile, let's say, and 2 or 3 major players evolved out of that, Apple, Android, and some would say a few others. That allowed us all to code in the same way, to kind of understand what needs to be done in the same fashion with 1 or 2 different providers. We don't have that in robotics. Like, there's not a big player saying, here, I'm going to provide actuators, and here's the standard, here's the schema for this actuator. Like a Matter, if you heard of the Matter protocol for homes. There's a defined schema, and every IoT device understands this schema, and they can all talk together, interact, right? We don't have that. And so it's going to take a major player, the Agilities of the world, the Teslas, Boston Dynamics, say, hey, this is our standard, and if you want to follow it and be part of the ecosystem, then it'll work. But then you also have to lower the cost of that actuator that you're going to sell us.
Yeah, I mean, the standards, that's a big thing. I mean, I always think of like ROS. A lot of people love and hate ROS. Well, most people love it. And that it's really what it stands for. Like, it's like, this is a way to interact with robots, and also a lot of academia likes that, because it's like a place we can say, hey, that's a good standard to go by. But I'm also, like, I'm always like skeptical also of like if there's going to be a plateau. So like once this stuff is figured out, like you have models or solutions to problems that are like, agility based or like sensory based, that are, well, this is the best vision, this is like relatively the best, motion algorithms, and they'll like, okay, that's the de facto standard. It doesn't make sense to, I mean, there'll always be somebody chipping away at another project, but it will help industries move forward. But at the same time, like, business-wise, there'll be a lot of winners. Sometimes, like, also, like, some businesses won't make sense. Like, there'll be some, like, chatbots right now. Like, a lot of people, oh, this is so fascinating, it's great, you can talk to a chatbot, but, like, there's social implications, there's, what's the point of having like an Alexa or something that can talk to you? It's fun. You pay for that every month, like a Netflix subscription, if it's the smartest thing, but it's still just a puck. It's not an action robot. When you do get the action humanoids that are walking around the world, like interfacing with people, that's where it gets more interesting, but I'll give it like at least 2 years. How about that?
Well, to your point a little bit about that, I mean, I think you mentioned hallucinations and stuff, and there's some unpredictability inherent in these systems, but we haven't really seen how that would manifest in the physical world, and I'm just curious, what is that even going to look like?
Well, we have seen it because Tesla is a robot, right? Tesla car, and it was fully capable of hallucinating and telling you one thing and actually meaning another, and that can be very, very dangerous. So they put controls in place to say, all right, if this happens, fall back on a redundant system, and if that happens, fall back on a redundant system. So in my estimation, I believe that we're going to have these framework models, we're going to have a control plane that's on top of all these things that says, does this make sense? before we actually give that action out to, and then actually, I think Gen AI, if you're going to think about it in that context, would be more higher order commands and actions, like go to that other room. And then you, on the model running on the robot, would then navigate its way over there safely using all of its sensory data, because Gen AI is actually pretty slow when it does its inference. So even the fastest generative models are relatively slow to actually actuate the robot and get in all the inputs.
O1 has much more higher accuracy in some ways because it's running the same thing through itself and taking the best answer, but it's obviously takes longer. So my guess is we're going to have a hybrid of a reasoning type of model that's helping whatever we're driving think through what to do, and a more moment-to-moment model with a much higher frequency that's telling it how to do the thing, is my guess, but I think it's still early. Y'all probably know more, have thought about that more than I have.
Very early.
Well, I mean, so Jim Fan, who was here earlier, right, with the NVIDIA team, right, they've been pushing this like system 1, system 2, thinking fast and slow dichotomy of a model hierarchy where you have higher level reasoning and then you have, faster, execution planes, right? And I think we are seeing that kind of hierarchy and stack work really effectively across robotics. Certainly at Agility, as you talked about earlier, we have that kind of time-based discretization of like the lower order, slow thinking, and the higher speed sort of reactive planning and execution framework. I think in both we see hallucination manifest in various ways, really as world state evolution, right? What you can see is inconsistencies in world state, either at the reasoning level where the robot says, I will put this garbage bin into itself, which is obviously not a world state evolution that can occur, or in something like a motion diffusion policy, you'll see the robot folding, I saw this at a robot demo earlier this year, one of the many towel folding demos that we get to see these days. The robot was basically just folding air for a while, and then it picked up the towel and started folding the towel. And that's the similar manifestation of an incorrect world state evolution at that layer. So we do see it, it's there, and it needs to be solved for. I think one interesting thing is, what's the implication? Like if the robot folds air for a minute, like that's kind of fine as long as overall it can still do the job, to the earlier talk just before this, right? You could fold towels all night, and as long as you get them done, like that's fine. It's separate from safety concerns, and we can kind of separate those out, where as long as the things that the robot is doing are within some envelope and you've got a safety system around that as a guardrail, it may be okay for generative AI to be non-performant, within that space. Again, as long as you're meeting the product requirements. So I think that's how we can kind of phase it in, is it's okay for it to do things as long as it's got the guardrails where if it does have a type of hallucination, the effects of those are simple and non-critical. Like maybe it takes a little bit longer to do the task, or maybe it drops a towel, but that's okay because it's a towel and that's a fine thing to do. So I think we can still work within that framework.
I kind of fall back to just-in-time simulations and the real, when things don't go or don't seem like they're going to go as planned, or something is an undiscovered area and inference is happening, then that's an area I think where you should expand, but trying to just understand whether the model is going to be successful before we actually execute it on the robot. Yes, it might take longer. You might require more compute or cloud compute, et cetera. But the reality is then you can ensure that the next action you're about to take is going to be somewhat okay, right? As much as you can.
Right. If you have a question and you want to raise your hand, hopefully we can bring some mics around. And I just want to ask one more thing as that happens, which is something that we brought up a little bit, but I want to drill a little bit deeper on, which is just that to make progress here is going to take a lot of data, and people are collecting that data, but it's a lot of industry that is collecting the data, and everybody realizes just how much value is in that data. And I've talked to robotics companies who do something practical with a robot, and they're making money at it, but they understand that their primary business is the data that they collect. So as we're trying to scale all this stuff and teach robots to do interesting things, is there a way to be collaborative, or is it just going to have to be because of the value there that everybody has their own data, that they train their own model, and then that is their business.
Maybe it's naive, but this is my own personal opinion. It seems that if we can find a way to inform the models, the foundational models with the data, if there's a way to do that, then it's very likely the foundational models will be better for the field. How to go about that in a way that's good for everyone, I think is an interesting question. But I'd really like for the models to be really good for everyone and to be able to use, the field to be able to use the same models. And so that's, I think, a key question.
I would say I'm a shamelessly plug Rob from Robot Studio, who's open sourced a robot, and the idea is to collect that data from these various permutations of that robot, and then feed that back into the communities. A shameless plug, but I do think that's something that we can do more, share that data, and this makes everyone better. I will say that for the first time the robot's in the home and it falls on a person, we're all set back. So we have to be sure to get it right across the various companies that we have. So the only way to do that is sharing data.
I think for us, it's a little bit of we have to collaborate, and there's also stuff that's unique to our robot. And I think going back to how foundation models are going to be used, it's highly likely that we're going to have to collaborate on those base models, and then we're all going to fine-tune them to our own platforms and our own use cases and so forth. And so we do need to figure out the right way to collaborate, because we're not building our own large models. We don't have enough data on our own to do it, but we are building our own small models, and we're certainly fine-tuning existing models from the open source community and from proprietary models that we're partnered on. So there is that sort of necessity to share, but also there is a sense of ownership once you actually get down to getting those things to work on the robot. So I think you can have both, and that can still be a healthy industry.
Yeah. Really quick, just a scary thought too. Like, what if the government gets involved and they want to make it open? They make everybody play together. It
always goes well when
interesting. But academia usually is where it's like a grassroots uprising. I think a lot of industry happens and great solid products happen, but then everybody's always looking for the lowest common denominator and make it cheaply. So, some scrappy kids eating pizza some night will be like, let's just make a whole bunch of crazy dynamic models and figure this out. Or who knows, maybe there's some weird hacking thing that will happen. Crazier things have been done. Not saying, not endorsing that.
All right, questions?
You talked about the data format standardization. You talked about the data format standardization. What kind of organization do you see or feel will be most appropriate to actually standardize the various different data formats?
I can tell you that for a second and pass it along. I think Safety Standards Board is going to be the primary place where we can all agree safety is most important. So if things come out of those, like ISO standards, things come out of that, then you're more likely to have to adopt it. You have to agree at that point. I think we should try to come up with our own standard amongst us companies. We're starting to see collaborations like OpenUSD for how we handle models, and Pixar and NVIDIA and Apple and Amazon and others are working together on that. I think that's the way we go, is we try to, and like I mentioned before about actuators, those kinds of things, to take an actuator and replace it with another actuator is largely impossible today without some kind of code. As people start to sell these things in mass, you might see some standards erupt out of that.
I think we're in part taking the lead of some of the folks that are building the larger models, like certainly looking at what is being ingested from data sets like OpenX embodiment, what folks like DeepMind and OpenAI and other players building large models have been able to ingest to create successful multimodal models. That's giving us the hints for what data representations we should be building our own data lake of. So I think that's kind of what we're looking to sort of build upon. And I think as we spend more time with this, and like other players like physical intelligence are kind of sharing what works and how they're building up their diversity of data sets, I think there's a lot of sharing that can go on there in terms of figuring out, well, what are the best modalities of data, what's really relevant, what can be compacted out, as we're collecting stuff. But in the meantime, we're just building a data lake of just like everything ever, and we'll project it down later once people sort this out.
Collect all the data, all kinds of data, even if it doesn't even make sense to you, because likely we can use it.
And we don't know exactly what is actually going to be important. I think that's the tricky thing. I think that the instinct is to say, oh, we can take this SLAM data and vectorize it, or like something like that. But it may be that actually raw data or unsimplified data is more valuable to the model. So that's something I'm interested in watching to see what happens.
Yeah, I guess my question's very much along these lines. I'm kind of wondering if actually the data soup might be better. I don't know, like when you go downstairs, I went down during lunch, the computers that you see from the Altair to the PDP, to the Apple II or the Commodore, everyone has a different user interface, and a different kind of readout. And some are analog displays, some are digital. But as a human, we can, and especially as we become familiar with those, we can read any of them. And perhaps the more that we see, the more examples, the more visualizations, the more we understand all kinds of things. I don't know, I'm going off of nothing beyond intuition, but I'm just curious, like, maybe actually all this random raw data with enough training and compute will something will come out of it.
Yeah, you can use Gen AI to map data. So we were just talking about this earlier, mapping a 5-finger hand to a 3-finger hand is actually an easy exercise with Gen AI. So yeah, give us all the data, and the part that's going to be kind of challenging is the sensor data is different. Like there's no 2 cameras that are the same, there's no 2 lidars that are the same. So you can't be exactly sure if your data from one thing is going to work somewhere else without it was a form of translation.
My sense is that a bit of standardization in the very beginning will help create a more functional model to start, and then expanding out will be easier, is my guess. But I think if you have enough data from different sources, that will work, but it might take 3 times as long. So it may be that if you can say, okay, well, if we use this field of view on our cameras, and we have this layout for SLAM, and we have this basic understanding of like the proprioception data, and this basic understanding of pressure data, and we start with that as a community, that these models get better much faster, but then they don't stop there. Then you can start to expand out, and the model can continue to be useful. But we'll have to see.
I think the thing that keeps me up at night is that we miss an important data channel. There was a really interesting talk at ICRA this year about, for example, using the audio channel from YouTube videos when building out these models to basically be a proxy for contact physics. If you're scratching against something, that actually tells you about something about the forces you're exerting in the world. And it's basically because YouTube doesn't have a force channel, right? It only has this audio channel. It's a crude proxy, but surprisingly effective. So when I'm thinking about, what we need to be doing here, one thing that I worry about is, we collect these data channels around stuff like maybe force or, depth data when we're using RGBD cameras is often, really underutilized or underrepresented versus RGB data. And so that's kind of more the thing that I'm interested in, is making sure that these modalities are preserved and conditioned appropriately. When we want to be able to then say, oh, like this was during a particular set of tokens style of operation, when we need to connect that up to being able to then regenerate that particular intent. Like, oh, this was a cooking task, or this was a, in our case, we can tie it to the task execution information that we had at that time. So that's what I really mean about it being important to figure out what's relevant.
Even IR data, you can get from almost every camera, but you have to remove the filter. And so that kind of thing is actually incredibly valuable. We found in VR, but we probably aren't in the field generally getting, IR data.
All right, well, we're gonna have to end here. I'm so sorry, but please give our panel a round of applause. Right now, now we have a networking break, so please be back here in about 20 minutes at 3:10 for the final sessions. Thank you.